Okay, so last question, question 4. Considering only filter A, determine the order of the filter, the type, and the cutoff frequency FA. So the order of the filter, if I'm not mistaken, it is given by the number of devices who are dependent on omega. So what do I mean? For example, the impedance of a capacitor depends on omega, right? See, J omega C, there's an omega. And then an inductor also depends on omega, so J omega L. So it also depends on omega. But resistors, no, right? They're not dependent on omega. See, it's just R. There's no dependence on omega. So no matter what the frequency is, its impedance doesn't change. So to determine the order of the filter, you count how many inductors or capacitors it has, and that would be your order. I'm not exactly sure about this. You might want to consult a professor about this, but I think that's the rough idea. So with that being said, considering only filter A, count how many inductors / capacitors you see. So we only see this, right? It's only one. So it's first order. Because it's one, then this will correspond to first order. Okay, now find the type. So this is something we've seen in tutorial before. To identify the type of the filter, first you must find the gain, the expression for the gain. So let us do that. Now, notice that this is called a cascading op amp or a composite op amp, meaning it's not just a single op amp, it's an op amp connected to an op amp again, so many times. So they've labeled the output, they labeled the input, but they never labeled the intermediate stage. Okay, so let us label it with V1. Okay, let's call it V1. Okay, so if I want to find the gain of A alone, I need to find V1 over V in, correct? Because that is the V out over V in for the filter A alone. So that's our objective. So let us go ahead and do that. That's our first gain. So first things first, for op amps, always use the three principles, right? The three properties of the op amp. So V plus equals to V minus, I plus equals to I minus equals to 0, and then KCL wherever possible. Oops, KCL wherever possible. So it doesn't make sense to do KCL here, right? Because it just doesn't make sense. And so we shall do KCL here, right? So I'll assume it goes this way and this way, right? You can assume it goes this way too, okay? Provided you write your KCL correctly. So current going in is equal to current going out. But for now, I'll write it like this. So going into the node will be this one, right? It goes into the bubble, and then going out of the node will be this one. See, it goes out of the bubble. So going in will be this guy. So what's the formula for the current going into the bubble? It will be V start minus Vn over R, right? Current is given by delta V over R. Delta V is given by V start minus Vn divided by R. So it starts at the in, it ends at the V plus, right? It ends at the V plus. So current going in is V in minus V plus divided by R1. Then what is the current going out? The current going out is, it starts from here, V plus, it ends at ground. So V start minus Vn is V plus minus 0 divided by, so divided by the impedance of the capacitor, which is 1 over J omega C1. Okay, so what should we do? We can drop away this 0 because it doesn't do anything. And then this, I will write it as J omega C1 V plus, right? So if you want to focus on this, if I have an expression which is 1 over A over 1 over B, like that, it's just the same as A times B, which is just AB, right? So this basically moves up here. Okay, so okay, I have this, I just copy it down. Okay, I shall move this to this side, multiply it to the other side. I shall get J omega C1 R1 V plus, and then I will group all the V plus terms together. So this, I will move it to the other side. I get V in is equal to V plus J omega C1 R1 V plus. Okay, what shall I do next? I shall factorize. See, both of these are V plus V plus. I shall factorize it out. So 1 plus J omega C1 R1 factorizing out V plus. Then remember, our objective is to find V1 divided by V in, right? It's the V in over V out. This is the gain. So if you do that, you shall get, sorry, let me check again. Yeah. So remember, see, look at this. This is V1, correct? And V1 is connected to the negative terminal of the op amp. So that means we know V1 is equal to V minus. But we know from op amps that V minus is equal to V plus. Okay, V plus is equal to minus. This is a property of op amp. And we know from the diagram V1 is equal to V minus. Therefore, we can say that V1 is equals to V plus. So wherever we see V plus, we can replace it with V1. Okay, so I can replace this with V1. Then if I make V1 over V in the subject, V1 over V in, I will get 1 over 1 plus J omega C1 R1. So this is our gain. Now, how to identify the filter type using the gain? Remember, we need to take the low frequency limit and the high frequency limit, and then check the results. So let us do the low frequency limit. So you take limit as omega approach 0. Remember, low frequency means it approaches all the way to 0. So you take the gain, which is this. Now, as omega approaches 0, this becomes 0, meaning this becomes 0. So what you get is just 1 divided by 1, which is just 1. So this answer is 1. Now let's take the high frequency limit, high F, limit as omega approach infinity, because high frequency means it becomes bigger and bigger all the way to infinity. So 1 over 1 plus J omega C1 R1. Okay, so as this approaches infinity, the whole denominator goes to infinity, right? So 1 divided by infinity becomes 0. So this approaches 0. Now let's check the results. See, at low frequencies, there's something. At high frequencies, there's nothing. So that means this is a low pass filter. Okay, as simple as that. So we've answered question 2. Now answer question 3. Cutoff frequency. So cutoff frequency, again, just from the tutorials, the concept is this. You must solve H, the magnitude of H is equals to this divided by root 2. So solve this for omega, and that should give you your cutoff frequency. Okay, so again, this gain, H, is what we got here, right? Which is this expression. So let us just put it in. 1 over 1 plus, 1 plus J. Oh, this is very ugly. Sorry. So 1 over 1 plus J omega C1 R1. Okay, this is our gain, is equal to. Now, what is our H naught? H naught is the non-zero limit. So you see, this limit is 0, but the other limit is 1. So this is our H naught. Okay, so it is 1 divided by root 2. Okay, now from this step onwards, check are the numerators the same. So remember, this modulus, I can split it to the numerator and the denominator. So I will split it to here and to here. Now, what is the modulus of 1? The modulus of 1 is just 1 because it's just itself. Now, are the numerators the same? Yes, they're the same. So that means I can equate the denominators. So the denominator states that the modulus of this is equal to root 2. The modulus of a complex number is given by the formula, this, and like that. Okay, this is the modulus formula for complex numbers equal to root 2. Both sides have square root, so I can drop them. Drop this, drop this. Okay, let me just move this away. Okay. Now 2 minus 1 gives me 1. And then I can square root both sides to get rid of square. And then make omega the subject. I should get 1 over R1C1, right? And don't forget, omega can be given by the formula 2 pi f, right? In this case, it's filter A, right? So they ask for FA. See, F subscript A. Okay, so FA is equals to, let me find my solutions. Sorry. Okay, my solutions tell me this is 159 kilo ohms times 1 microfarad. Okay, you make FA the subject, you should get 1.00097 hertz. Okay, so it's a very small cutoff frequency. Oops. This is for later. Okay, so next, what do we want? Okay, now we need to do the same thing, but for filter B. And I tell you, it's exactly the same. Why? Because the configuration is almost the same. Now let's take a look at this. Look at filter B. It's structurally the same as filter A. So you can already tell that the whole process is gonna be nearly identical. But I'm just gonna do it anyways for completeness sake. So determine the order of the filter. Again, there's only one, if you check, there's only one capacitor, so I'll just say one. So therefore it's first order. The type of the filter, again, first you need to find the gain. After you find the gain, you take the limits. From the limits, you check the results. Okay, so let us just go ahead and do that. So what can I say? So to find the gain of this filter, our objective is to find V out divided by V1, right? V out divided by V1. So this is our gain of filter B. First things first, we need to find KCL wherever possible, right? So assume this direction, in this direction. So for this current, what is the current? Sorry, we're doing the KCL for this node, correct? So what is the current for current going into this node? It is V start minus V end. So it's V1 minus V plus. Okay, so let us write that down. So V plus minus V. Sorry, it starts with 1, right? Then ends at this divided by R2, I believe. Yeah, R2. Now, what is the current going out of the node? So the current going out of the node is, it starts at here, V plus, it ends at ground. So V plus minus ground, 0. So V plus minus ground divided by the capacitor it goes through is 1 over J omega C 2. Okay, so drop away this, simplify this, this becomes J omega C2 V plus. Then I'll multiply this to this side. So there should be a R2 here. Yeah, I'm just doing this quickly because it's exactly the same thing as A. Then I shall move this to the other side and factorize it. So you get 1 plus this equals to V1. Then we know from the diagram, correct? The diagram shows that V out is just nothing but V minus. So V out equal to V minus, and we know V minus is equal to V plus. So wherever we see V plus, we can equate it to V out. So I change this to V out. Now I make V out over V1 the subject. I will get 1 over 1 plus J omega C2 R2. See, it's actually pretty much the same with the first filter. Okay, again, from here, take the limits. So limit as omega approach 0 for this. So as this approaches 0, this goes away, and then you get 1 divided by 1, which is just 1. And then the high frequency limit, 1 plus J omega C2 R2, as this approach infinity, the whole denominator goes to infinity. 1 divided by infinity is just 0. Okay. Low frequencies, there's something. High frequencies, there's nothing. So this is a low pass filter again. So low pass filter. Now to find the cutoff frequency, what do we need? We need to solve this. We need to solve the magnitude of h is to the maximum h divided by √2. Okay, the maximum h is given by this, right? Because this is 0, and then the other value is the maximum frequency. So this is this √2. Then h is this 1 over 1 plus j omega c2 r2. Then I can split this modulus. So split this modulus. Split. Modulus of 1 is just 1. Numerators are the same, so I can equate denominators. Okay. Sorry. Sorry, children. Okay. Then you repeat the stunts that we did earlier. So square root of 1 square plus this whole thing square equals to √2. Squares can drop. 2 minus 1 is just 1. And then you take the square root of that. You should get 1 omega c2 r2. It means omega is this 1 over r2 c2. Then omega can be written as 2 pi fb equals to 1 over, what's fb? This time fb is 1.59 kilo ohms times 100 nanofarads. Then you solve for fb, you should get 1000.97 hertz. Okay, so this is the cutoff frequency. And what's next? Okay, so we're done. Okay. Determine symbolically the frequency V out over V in for the whole circuit, right? So again, this is the same as the last tutorial. So for the entire circuit, what do we need to do? V out is here, V in is here. To find the gain of the entire system, you take the gain of the first system multiplied by the gain of the second system. Again, to recap why, right? V out over V in. See, the gain of the first system is, sorry, let's start with the second system. The second system is V out divided by V1, right? This is V1. So V out divided by V1 multiplied by the gain of the first system. So the gain of the first system is V1 divided by V in. So V1 divided by V in. See, look, these two can cancel, right? This cancels with this, giving me V out over V in. Indeed, it is. So that means we need to take the gain of the first system, sorry, the gain of the second system, times the gain of the first system. It doesn't matter, right? Gain 1 times gain 2, gain 2 times gain 1. It's just the same thing. So with that being said, let's just do that. So we know that V out over V in is given by the gain of 1 times the gain of 2. Gain of 1 is given by, okay, from earlier, just now we got this omega C1 R1 multiplied by 1 plus j omega C2 R2. And this is your answer. Okay, you can simplify it further. Fine, I'll simplify it. Okay, I'll simplify it. So this becomes 1 over 1 plus j omega C1 R. Woo. R1 1 plus j omega C2 R2. Okay. Now determine the output voltage as a function of time. Blah 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 blah. Okay, so how do we do this? They want what they are asking for is V out, and what they give us is V in. So remember from the previous question, this gain is given by V out over V in, right? So that means we can make use of this to find V out because they give us V in. We know this gain, so that means we can find V out. Therefore, V out is given by this entire gain multiplied by V in. So now we have to plug in the numbers. So V in is given by this, right? So we have to change it to a phasor. So V in as a phasor is 7 at an angle of 0, right? Because remember, if it's in the format of 7 cos 2 pi tan t, it's actually a phase of 0 here. So I just take the amplitude and then I take the phase. So that's my V in. Okay, then you have to plug in all the numbers here. So V out is equals to, okay, this is tremendous. 1 plus j times, okay, what's the omega here? The omega follows from the source. So this omega is actually this omega, right? 20 pi, it's actually 20 pi. So 20 pi. Okay, then multiplied by, oh wait, sorry. Yeah, then multiplied by your V in, which is 7 at an angle of 0. Okay, you punch this all in your calculator. I know it's a bit tedious, but it is what it is. Then you will get a phasor of this. Okay, I'm doing this in degrees, right? You might be doing this in radians, depending on your calculator mode. And then to change this to time domain, you just copy it down. So in time domain, copy the amplitude, cosine, and the omega is 20 pi t. Then you copy down the phase. So 84.85. Okay, just a recap. Where did I get this omega? Where did I get this omega? It's just borrowing the omega from the V in, which is this one. Okay. It makes sense that it's really small, right? You see, notice that this amplitude is kind of small, 0.697, because earlier we got a cutoff frequency of 1.00097 hertz, remember from the first question? And this is a low pass filter, right? Yeah, it's a low pass filter. Okay, so that means beyond this, it will start to drop to 1.0097. Now, what is this frequency in, what do you call this? Okay, this is omega. So omega is 20 pi, which you know is 2 pi f. So what's the frequency in hertz? It will be cut, 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 cut. This will be 10 hertz. So you see, where's 10 hertz? 10 hertz is somewhere here, you know, it's beyond this 10 hertz. And remember, cutoff frequency means beyond this value, it will start to taper down to a really, the gain will start to drop to a super low value. It's close to 0, but not quite, right? See, that's why it's 0.697. It's kind of close to 0, but not quite yet. So yeah, expect it to be really small because it's already beyond the cutoff frequency of the first filter. Okay, so that's just to give you an intuition of why is this so small. It's kind of suspicious, right? But it is because it's being filtered out by filter A. Okay, I think that's it, right? Yeah. Let me check again. Oh yeah. Okay. So with that, we've finished 21, 22, Sem 2 in a nutshell. Okay. So what this QR shows is a feedback form that not many people have done last semester, because I think I never made a public queued announcement. So here I'm gonna do so. So this leads you to a feedback form where you can criticize me, insult me, or whatever you want to do regarding my PTP throughout SEM, yeah, throughout the SEM. Or you can just do it based on my YouTube videos, which a lot of people did if they never joined the PTP. Yeah, so I just want to make this series of videos because a lot of people have reached out to me, and it's just random. So like when I go to school, a lot of people would just say, "Hey, you did the PTP, right?" And then they were really thankful for it, and it really makes my day. So I'm glad that I can make your semester. Yeah, so yeah, so I just wanted to show that PPP never dies. If I had to put it bluntly, I hope I can continue this in future semesters. But yeah, so good luck for your finals. It's coming around the corner. It's already week 11. It's gonna be quite quick. Um, yeah, see you then.